Hello my dear young friends, welcome back to C level physics. I think all juniors might have completed your exams successfully. So today in this video I would like to explain what is meant by compound pendulum, what is meant by physical pendulum. Of course both one and the same. So either physical pendulum otherwise compound pendulum. Right. Now what is the period of oscillation of this physical otherwise compound pendulum? Right. So first of all, what is meant by compound otherwise physical pendulum? See here, any rigid body of any shape when it is hinged at some point and is made to oscillate about a normal axis passing through that hinged point is said to be physical pendulum otherwise compound pendulum. See here, no restriction for the shape of the rigid body. So, but only the criteria is it is to be hinged at some point and is made to oscillate about that point. So then the oscillations made by that hinged rigid body is said to be simple harmonic in nature. Now what is the period of oscillation of that physical pendulum or rigid body or compound pendulum? Let us see. See here, as there is no restriction for the shape of the body, I can take rigid body as of any shape as shown in figure. Suppose here it is one rigid body like that. This is what one rigid body which is hinged at some point here, right? See, it is made to oscillate about a normal axis passing through hinged point. So it is made to oscillate like that, about the hinged point, right? Now what is the position of center of gravity? This is the position of center, for example, G1. When it is at mean position, equilibrium position, G1 is the position of the center of gravity. Now, what is the distance of center of gravity from the hinged point? That is D. D is the distance of center of gravity from the hinged point, right? Now, during its oscillation on either side of the hinged point, right, at some instant, now this will be the position of the rigid body line. This will be the position of the rigid body. Same body, but made to oscillate at some instant. Let it be the position of the rigid body. Now, see here, this is what D. In fact, D here. This distance is D. Now, during its oscillation, definitely G, center of gravity, rises through some amount. See, this is what the position of center of gravity, for example. G2. For this orientation, let G2 be the position of center of gravity of the same rigid body. Now see, now center of gravity moves through a distance x like this, horizontal, from this vertical. See, let x be the distance, horizontal distance moved by this center of gravity, right? Now, what is the distance of center of gravity from the hinged point? Now, this will be the d again. D again. See, this is what D, here also D. What is D here? D means the distance of center of gravity from the hinged point. See, this is the distance. Now, when body is turned through some angle theta, again the distance of center of gravity from the hinged point is D only. So this is also D, from here to there D, but this is the height through which center of gravity rises. See, this is the height through which center of gravity rises, right? Now here we have one right angle triangle here. See here 90 degrees. Therefore from this right angle triangle we can have sin theta equal to sin theta is equal to opposite side by hypotenuse x by d, implies x equal to d sin theta. X equal to d sin theta. Okay, it is deviated through some angle. See here, body is turned through some angle here about the hinged point, but again it comes to its previous position because of restoring torque. Because of some restoring torque. What is the nature of restoring force or torque? To bring the body or particle back to get back to its previous position. So because of some deflecting torque, it goes away from the vertical, but because of some restoring torque, again comes back to its previous position. See, what is the turning effect here. See, body is going to turn in clockwise about the hinged point. See, in anti-clockwise like that. Body is turned in anti-clockwise like that about the hinged point, right? But because of restoring torque, again it comes back. Now, what is the sense of restoring torque here? Clockwise or anti-clockwise? See here, deflecting torque is anti-clockwise, but restoring torque is clockwise. See about this, about a normal axis passing through hinged point. See, this is the direction of restoring torque, but this is the direction. See, the thumb, as per right hand thumb rule, the deflecting torque is along the axis of rotation, outward from the board. But here, restoring torque, see, restoring torque also acts along the normal axis, which is passing through hinged point, but normally inward. Restoring torque is normally inward as per right hand thumb rule, but the deflecting torque is normally outward along the axis, right? So both opposite each other, right? So what is the expression for restoring torque? Restoring torque in the sense which tries or which brings the body to get back to its previous position. Tau restoring is equal to, right? Restoring in the sense negative, that is opposite to the angular displacement theta. Therefore, tau restoring equal to force into perpendicular distance. What is the force here? See, for this position, the body is acted upon by gravity. Means what is the value of gravitational force here? Nothing but mg. Weight acting on the body is mg. That's what gravitational force. See, this gravitational force is at a normal distance x from the line joining G1 and hinged point. So therefore, x will be the normal distance from the vertical and mg will be the force. See, these two are perpendicular to each other, x and mg. So here, F means what? Mg. Here mg serves as restoring force which causes some torque about the vertical. So therefore, F means what? Mg. That is minus mg into, what is the perpendicular distance here? Perpendicular distance in the sense the normal distance of weight from the vertical, that is x. So r perpendicular in the sense x. So tau restoring equal to minus mg into x. Again, x means what here? D sin theta. X equal to d sin theta. That is equal to minus mg into d sin theta. Right? So, if body makes oscillations with smaller amplitudes, then sin theta almost can be taken as theta. So, this is what one approximation which we should come across, that is tau restoring equal to approximately equal to minus mg d into theta. So instead of sin theta, we can take theta when rigid body oscillates with the smaller angular amplitude. So therefore, sin theta almost equal to theta, right? So under equilibrium, restoring torque numerically equal to deflecting torque. What is the torque which makes the rigid body to deflect here? Means tau equal to I alpha. So tau deflecting is equal to tau restoring. Tau deflecting equal to tau restoring. What is the expression for tau deflecting? I alpha. Moment of inertia of the rigid body into angular acceleration. Tau equal to I alpha. I means moment of inertia of the rigid body. Alpha means angular acceleration. Equal to tau r equal to restoring torque equal minus mg d into theta, not d theta, d into theta, right? Okay, now alpha is subjected, that equal alpha equal minus m g d by I into theta. This is what condition of angular SHM. It's not linear SHM. In case of linear SHM, A equal to minus omega square into x, but here it is alpha equal to minus omega square into theta. So compare with condition of angular SHM. Angular SHM, that is alpha equal to minus omega square into theta. See, alpha cancel, minus cancel, theta cancel. We left with omega square equal to mg d by I. That is omega square equal to mg d by I implies omega equal root over mg d by I. Right? Now, what is the expression for time period in terms of omega? Time period t equal to, we know that t equal to 2 pi by omega. That is 2 pi into 1 by omega. 1 by omega means take the reciprocal, that is I by m g d. So this is the expression for period of oscillation of compound pendulum, otherwise physical pendulum. That is t equal to 2 pi into root over I by mgd. If it is simple pendulum, t equal to 2 pi into root over L by g, but here it is root over I by mgd, where I is moment of inertia, m is the mass of the rigid body, g is the acceleration due to gravity, and d is the distance of center of gravity of the rigid body from the hinged point. That's what I want to say, right? Now, in case of circular ring, see here, in case of compound, otherwise physical pendulum, we can take any rigid body of any shape. It may be ring or it may be half ring, otherwise it may be uniform disc, otherwise it may be rod, etc. Right? No restriction for the shape of the rigid body. So we can have any compound pendulum, right? So in case of, see, for ring, if I take ring, that is ring is hinged like that about this point. Now going to oscillate above the hinged point. Now I equal to, what is the expression? When a ring is made to oscillate about a normal axis passing through one end. So here ring is hinged at this position. Now what is the expression for I? Means I equal to 2mr square. 2mr square, where m is the mass of the ring, r is the radius of the ring. 2mr square. So moment of inertia of a thin ring about a normal axis passing through one end is given by 2mr. We have to substitute 2mr square here. In case of for disc, if I take one disc, uniform disc like this, uniform disc. Now this is also hinged somewhere here. Now what is the mass of the ring here? Mass of the disc, capital, radius capital. Now it is going to oscillate about the hinged point. Now what is the axis of rotation? A normal axis passing through hinged point like this, right? Passing through one end, normal to its plane. So here also I equal to, in case of disc, that is mr square plus mr square by 2 plus mr square. So therefore 3 by 2 mr square, 3 by 2 mr square, 3 by 2 of mr square, right? 3 by 2 of mr square, right? In case of rod, for rod, in case of rod, suppose a thin rod of mass m and length L is hinged at one end like this, hinged at one end like this. So this is the hinged point. Now is going to oscillate about a normal axis passing through hinged point. Now what is the expression for moment of inertia? See, moment of inertia of a thin uniform rod of mass m and length L about a normal axis passing through one end is given by I equal to ml square by 3. I equal to m L square by 3. ml square by 3. So that's how, as per the shape of the rigid body, we can have different expressions for moment of inertia in finding period of oscillation, right? Now I want to derive an expression for period of oscillation of half ring, which is very crucial as far as advance is concerned and also mains is concerned, right? Oscillation of, period of oscillation of half ring, but expression is same only, t equal to root over I by mgd only, but I means we have to substitute the value of moment of inertia here, right? Okay. Period of oscillation of, period of oscillation, that is time period. Period of oscillation of ring. Right? Period of oscillation of ring. Right? So we can start from the expression itself. 2 point root over I by mgd. But we have to find I value before substitution of the form, right? So period of oscillation of ring. See, this is the ceiling. Now this is what offering, like this. This is what offering, right? Is going to oscillate about the hinged point. See, this is what hinged point. Offering like this. Offering. Now what is the radius here? R. From here to there R, here to there also R. See, if you consider one complete ring like this, center of gravity, otherwise center of mass, lies at its center, right? Where it is cut into two pieces, two equal halves, implies that for upper portion, mass distribution is not uniform. Of course, uniform on the periphery, but it is cut into two equal halves. See, with its full form, center will be the geometric center will be the center of the uniform ring. But when it is cut into two equal halves, now here no mass here. So actually this will be the position of center, but because of distribution of mass, center of mass shifts to some point here. That is to a distance of 2r by pi. 2r by pi. For lower portion also, see, for lower portion like this. For lower portion also, center of mass shifts to a distance 2r by pi. Right? This will be the position of center of mass. Right? So with its full form, geometric center will be the position of center of mass, but when it is cut into two equal halves, center of mass shifts to a distance 2r by pi from the geometric center. Okay, right? Inward, shifts inward. Here also shifts inward to a distance of 2r by pi. Right? So in the same way, see, this will be the previous position of the center of mass with its full form. But when it is cut into two halves, center of mass shifts to a distance 2r by pi here. Now what is the distance? See, this is the position of center of gravity or center of mass. Right? Now this will be the distance of center of gravity from the hinged point. See, this is the hinged point. This is the position of center of gravity. Now this distance is shift in the center of mass. That is 2r by pi. This is r. This is 2r by pi. This is d. Now this is what 90 degrees. From this right angle triangle, we can write d square equal to r square plus 2r by pi whole square like this. Right? So d square equal to r square. D square equal to r square plus 2r by pi whole square. From Pythagoras principle. That is d equal to root over r square plus 4r square by pi square. Now if r square is kept outside, it becomes r. Therefore ultimately d equal to r into root over 1 plus 4 by pi square like that. Right? So we have d value. We have d value. We have I value. What is the moment of inertia about an axis passing through one end? About a normal axis passing through one end? With its full form, what is the moment of inertia here in case of ring? 2mr square. Even though some portion is cut, but still moment of inertia equal to mr square only, if provided m is the mass of offering. Therefore I equal to offering also. For offering also I equal to, if m is the mass of the offering, then the same expression only, that is 2mr square, 2mr square. So we have both d and moment of inertia. Now substitute in time period, that is t equal to 2 pi into root over I by mgd, that is 2 pi into root over I means what? 2mr square, 2 capital M r square, for example, divided by capital M into G into D. D means what? R into root over 1 plus 4 by pi square. Right? Like this. Now cancel, R square, R cancel. Now we left with that is a 2 pi into root over, here are taking LCM, pi square plus 4 by root pi square goes to numerator, it becomes pi. That is 2 R pi by G into 1 by root over pi square plus 4. So this will be the expression for period of oscillation of ring. So that's how one can find period of oscillation of ring. Not only for half ring, you can find period of oscillation of any rigid body, otherwise any compound pendulum, otherwise any physical pendulum. Okay. Next, advanced model sum, that is mean kinetic energy of oscillating rod. Mean in the sense average. So during the oscillation of one rod, what is the average kinetic energy in a given interval? That is, see the sum here. A thin uniform rod of mass capital M and length L performs small oscillations about a horizontal axis. See, this is what horizontal axis. See, this is hinged at this position. So this is a normal axis passing through hinged point. About this point, otherwise about this axis, it is going to oscillate like that. Okay. So it performs a small oscillations about a horizontal axis passing through its upper end. Like this. Find the mean kinetic energy of the rod during its oscillation period. Find the mean means average. Find the average kinetic energy of the rod during its oscillation period. If it at t equal 0, so here the position of that rod is given like that. At t equal 0, it is deflected from vertical by an angle theta naught. See, it is not mentioning that it is not revealed that theta naught is as angular amplitude. So that's why theta naught is the angular position at some instant t equal to 0, but it is not equal to angular amplitude, right? So by an angle theta naught and imparted an angular velocity omega naught. See, it is going to oscillate with an angular velocity omega naught, but theta naught is the instantaneous angular position, but not equal to angular amplitude. So that's what we need to know. So solution, see, theta naught means angular position, not equal to amplitude, So we have to consider another symbol for angular amplitude. Let be theta naught. Let theta naught be the angular amplitude. Right? Next, what is omega naught? Angular velocity. Omega naught is given that angular velocity, given as angular velocity, right? Now what about angular frequency? Let be W, omega. Let omega be the angular frequency. What is the expression for angular frequency? We know that T equal to 2 pi root over I by mjd. So T equal to 2 pi root over moment of inertia by mg into d. D means the distance of center of gravity from the point of suspension, otherwise hinged point. See, this is the hinged point, this is center of gravity g. Now what is the d here? D equal to half of the length, that is L by 2. So in case of uniform rod, center of mass lies at its geometric center. Therefore, from one end, it is equal to L by 2. So D equal L by 2 here. So no need to give, but L is given. So as it is uniform rod, D equal to half of the length. That's why. So distance from the hinged point to the center of gravity. Right. So implies that omega equal to 2 pi by capital T. That is equal to 2 pi by T means root over mgd by I. That is omega equal to mgd by I, root over mg. D means L by 2 by I means What is the moment of inertia of this rod about a normal axis passing through one end means ml square by 3. That is ml square by 3. ml square by 3. So t equal to, omega equal to mm cancel here, ll cancel, that equal to root over 3g by 2l. So ll also cancel. L square cancel, 3g by 2l. So omega equal to 3g by 2l. Right? Now ultimately we have to find the average, otherwise mean kinetic energy within one oscillation. So in case of linear SHM, what are the expressions? V equal to omega into root over a square minus x square. Alright? Linear velocity equal to angular velocity into root over a square minus x square. Similarly, average kinetic energy in case of linear SHM equal to 1/4 m omega square into a square. A means angular, A means amplitude, linear amplitude, x means angular, it's a position of the particle, linear position of the particle, x means, A means linear amplitude, omega means angular frequency, m means mass of the body. In the same way, in case of angular SHM, so expressions can be modified as follows. Instead of linear velocity, you have to consider angular velocity. What is angular velocity here? Omega naught. So V is replaced by omega naught equal to angular frequency. Here also same symbol, that is omega only, omega root over, instead of A linear amplitude we have to consider angular amplitude, that is angular amplitude means theta naught. So theta naught square minus, instead of x means linear position, that is linear displacement. Here we have angular position, otherwise angular displacement, theta. So theta square, x square means theta square, right? So that is the modified expression. So as far as kinetic energy is concerned, in case of angular SHM, kinetic energy equal to 1/4. Okay. Instead of mass, we have to consider moment of inertia I. Mass is replaced by I. Omega as usual, omega square into A is replaced by theta naught. So theta naught square, theta naught. So this is the ultimate expression which we need to follow. That is average kinetic energy in case of angular SHM is given by 1/4 I omega square into theta naught square. So omega square, we have omega value from which we can find omega square. I also there, but theta naught square. See here, theta naught square, right? So average kinetic energy is given by, see here, average kinetic energy is given by 1/4, right? So before that we need to consider that formula. That is, what is theta naught, theta square here, that is theta square, or otherwise theta naught square. What is theta naught square? See, this is number 1, this is number 2. So one implies, see, omega naught square by omega square equal to theta naught square minus theta square. Theta naught square by theta square, right? Sorry, what is angular amplitude here? Angular amplitude, angular position means theta naught, sorry, angular position means theta naught, but angular amplitude is theta only, theta. See, in the given some theta naught, the symbol theta naught is for angular position, not for angular amplitude. So theta naught is angular position, theta is the angular amplitude. So accordingly we can change. Angular linear amplitude is replaced by angular amplitude, and linear position is replaced by angular position line. Right? Here also theta square. Right? So now one implies omega naught square by omega square equal to theta square minus theta naught square. Theta square minus theta naught square implies theta, angular amplitude theta equal to root over omega naught square by omega square plus theta naught square. That is that is theta equal to angular amplitude theta equal to root over omega naught square symbol, given symbol, so no need to change, modified, divided by omega square. What is omega here? Root 3g by 12 on squaring 3g by 12, but here 1 by omega square means 12 by 3g, so into 12 by 3g, 2 capital L by 3g plus theta naught square. So this is the expression for angular amplitude number 3. Now 2 implies we need to find kinetic energy, that is 1 by 4th I omega square into theta square. So kinetic energy, see here kinetic energy. So kinetic energy, average kinetic energy in case of angular SHM is given by 1 by 4th I omega square into theta square. That is 1 by 4th into I means what? Moment of inertia of this rod about an axis, normal axis passing through, one end equal to m L square by 3 into omega square. What is omega square here? Omega square means 3g by 2l. 3g by 2l into theta square. Theta square on squaring, root will be gone. That is omega naught square into 2l by 3g plus theta naught square. Right? Like that is 3 cancel, L square L cancel. We left with 2 4 8. Here m g L by 2 4 8 into 2L by 3g, 2L by 3g into omega naught square plus theta naught square. So this is what ultimate average kinetic energy in case of the given sum. Okay friends, thanks for watching. Bye.